Okay, Bismillah ar-Rahman ar-Rahim wa salatu wa salam ala ashrafil mursalin Sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. Assalamu alaikum everyone. So today inshallah we're going to be looking at the extended Kalman filter. So this is the last lecture of the localization topic. Okay, and this is the most practical one. So in real life, this is really what you're going to be seeing. With regarding the studying of this lecture is technically heavy, so there's really a lot of formulas. However, they're really all based on the linearization, what we discussed last time, so I'll just do a recap of that. This is not included in the quiz next Sunday, inshallah. It's still included in the exam, and you have an assignment for it, okay, for next week. Okay, so this is already part of what you're going to be doing next week of the assignment. So recap. That this is the framework and the overview of the Kalman filter, the standard Kalman filter. And we start by some belief about the robot state. The state of the robot can be anything that we want. Okay, so it's usually something inside of the robot that we want to estimate. Usually that includes the position of the robot, the orientation of the robot, but also the velocities. But even it can have more stuff. Today we're going to be seeing an example of how the state can even include more stuff than just the position and the velocity of the robot. And then we have a relation between how the sensors we're measuring, so the U, the control input, so one type of sensors, the proprioceptive sensors, how they are related to the state through the state transition model. And then we use this information to actually improve our belief about where the robot is or about the state of the robot. And then afterward, we correct that belief by another step, which is the correction update, using the sensor model. So we use here an observation from another sensor, which is usually an exteroceptive sensor. And in that way, we combine both of this information to always have a good estimate about where the robot is. Okay? These were the equations of the prediction. These were the equations for the correction. So you implemented this in the last assignment, and you played around with the robot in this toy problem to see how the Kalman filter behaves. We discussed also last time that there are some parameters here that you can actually play around with to tune the estimator. And these are here the Q and the R. So the Q here tells you how much you should trust the state transition model, and the R tells you how much you should trust the measurement when it comes. Okay, so how noisy it is. Usually these are covariance matrices, which tells the algorithm how noisy this information is. And by noisy, if you have something that's very noisy, it means that it's uncertain. If you have something that's less noise, that means that you are very certain about this measurement. And so this was in terms of a block diagram. You calculate first, you take the state estimate and the state covariance from the previous time step, you advance them with the prediction, and then you take the observation, you compute the innovation and the covariance of the innovation, so the beta and the S, and then afterwards you correct the state. So you correct here the state through the Kalman gain, and you correct the covariance again with the Kalman gain. And the Kalman gain is the most important part here of the algorithm, and it's usually also the most computationally expensive because of this inverse here that we have. And afterwards, we have a better state and a better mean and better covariance. So we started with a Gaussian. This is the belief, prior belief, and this is the posterior belief after doing the Kalman filter. And this is a recursive algorithm. So every time step, you just run it again and again and again. The main drawback of this Kalman filter algorithm is that it assumes we have a linear state transition model and a linear measurement model. And in real life, nothing is linear. Today we're going to be seeing a practical example for the IMU. The IMU is definitely not linear, and we're going to be seeing how we can extend the Kalman filter to that. The extension of the standard Kalman filter to the case when you have nonlinearities is usually called the extended Kalman filter. This is not the only version of the Kalman filter that can treat nonlinear systems. There are many other ones. This is the only one we're going to discuss. And the whole idea is that it will linearize the nonlinear models around the belief that we have, around the mean state that we already, from the prior step. So the linearization is simply the generalization or just an application of the idea of the Taylor series. So if you have any function f of x, I can approximate it by f at some point, x0, and then plus the Jacobian of the function f evaluated also at x0. So I get here in the end a matrix, an n by n matrix, assuming x is an n-dimensional vector, and you can multiply it by x minus x0. So this is Taylor series expansion. And we compute this Jacobian okay, so that we can give it to the extended Kalman filter algorithm. So that's the only thing that changes, okay, that we need to compute this Jacobian. However, we have multiple of these Jacobians. So f, the state transition model, is a function of x and u and v. Okay, so the previous state, the control input that we have, and the v, which is the noise. And all of these three variables can appear nonlinearly in the equation, and the Jacobian we need to calculate it with respect to each of these three. So the f here, the capital F, is simply the Jacobian of f, the small f, with respect to xk minus 1. And the b here, which is the Jacobian of f with respect to uk. And we don't use that, by the way. It's just I write it here, but and I mentioned also in the slides. We don't use it. We don't need it. You'll see in the algorithm we don't need it today. And the v, so the Jacobian of f with respect to the v is given by the G matrix. So this is the f matrix, simply just partial differentiation. This is the b, we don't use it, as I mentioned. And this is the G, partial f by partial v, and so on and so forth. Okay? So this is just how the matrix looks like. It's scary, but it's just something that you can very easily program. And in the assignment, you're going to see this is all implemented for you. But I totally suggest, okay, I totally recommend that you go into the code and look at how these differentiations were calculated. Okay. You also have a homework problem. It's a solved example. Okay, it's already on Blackboard that does the linearization for you. Okay, so this is where you can practice the linearization. Okay. And the linearization is nothing else than a partial differentiation. Okay, so this is from your math, okay, courses. So this is the Jacobians of the f. You also have Jacobians of the h matrix, of the h function. So we have capital H here is the Jacobian of h, small h with respect to x, and the L here is the Jacobian of the h with respect to w. Okay, so it's just the same matrix, the same calculations, all our partial differentiations. We just have two functions, the f, small f, and the big and the small h. And we have different states, we have different variables. So the x and the v and the w. Okay. So now how does the extended Kalman filter algorithm look like? Okay. We're gonna show you the extended Kalman filter algorithm side by side with the standard one, so that you can just compare and contrast both, and you can see what is the new stuff that we have in the extended Kalman filter. So, and by the way, whenever someone says a Kalman filter and just stops, it's meant by that the standard one, the linear version of the Kalman filter. Okay. When we say an extended Kalman filter, we mean these algorithms. Okay. So in the prediction step, okay, when we took the mean and covariance from the previous time step and we updated them, okay, by the control input u, this is how the Kalman filter was working. Okay, so it multiplied the previous mean by f, and it multiplied the u by the b, and then summed both to get this prediction. And we did something similar here to the covariance, but we just multiplied before and after by the f, and we add the q here, the covariance of the noise. So this is how the standard Kalman filter does it. The extended Kalman filter does the following. Okay? When it calculates the mean, okay, it uses the equation of the nonlinear model as is. Okay? So it does not do any linearization. It just uses the nonlinear model, because we can do it. We already have the equation, so we can just use it, and it will be much more accurate than doing a linearization at this step. However, when it's updating the covariance, it needs to use the linearization of this method, of this function. So you see here we have the f and the g here, and the f and the g are simply the Jacobians of this small f function. Does that make sense? Take a look at it and just try to understand it. This is very simple. Okay. If it's not clear, let me know. I can repeat it as much as you need. Okay, because the next slide will be more involved. Is that clear for everyone? Who wants to repeat it? Clear? Yes? No? Somewhat? Okay, compare both sides. Okay, before asking if this is clear or not. Is this clear? Yes. What you did in the assignment, right? So what we discussed in the Kalman filter. Can you explain this as an algorithm to me? Explain it as an algorithm. So what is the input and what's the output? No, as variables. What you get, for example, what you store in the code, and then you use them to calculate. What comes from as an input? Yeah, Muhammad.
The x is the initial.
This x hat
Which is
is the previous mean.
Yeah, and the u is the control input.
The u is the control input. And the p here, pk minus 1, it's the previous covariance matrix. So this is a mean of a Gaussian, and this is the covariance of the same Gaussian we're talking about. And after that, I take this Gaussian, which is identified by these two parameters, and I update the mean and the Gaussian by these two equations. And you see the only thing that's an input here is the u. And the matrices I use for this update are the f, the b, and the q. So what is the f, what is the b, and what is the q? Where do they come from? Where does the f, the b, and the q here come from? The f, the b, and the q. Anyone? At this, in the Kalman filter, the standard one, they're not the Jacobian. Okay. So the f and the b, they are the properties of the model itself, because the model itself was linear. If you go back to the state transition model, so here, you see the state transition model that we did, that we used in the Kalman filter, the standard one, was already a linear model. We did not need to linearize it. Okay, so the f was the relation between the xk minus 1 and the xk. The b was the relation between uk and xk. Okay, so the f and the b was already from how we modeled the system. It depends, of course, on the problem. Okay, we saw, for example, the 1D problem and the 2D problem. The f looked differently, okay, because it depends on the problem and how many sensors you're using and what type of sensors and so on. So it's, all of these matrices are problem specific, but the algorithm is general. So the f and the b, we got them from the model that we know, the mathematical model that we did for our system, and the q here comes from our knowledge about the noise of the input. And it depends on, actually, the q here, we can change it. That's exactly what you did in the last assignment. You played around with the q, and you got different performance of the Kalman filter. Okay? So f and b and q are matrices that you use or you give to the algorithm. Okay? So that's how these are used. Now compare this to the extended Kalman filter. What changed here? What changed in the prediction step of the extended Kalman filter? First, when we calculate the mean, what are we using here? What is this f? The state transition model, but the nonlinear version of it. So this was the state transition model, but the linear version. And this is the state transition model, but the nonlinear version. Okay? We're using the nonlinear equation that we have. So that's one. What about the second line? What are we using here? First of all, the second line is exactly the same as this one, right? What is the only difference here?
G.
The g, right? So we have this before and after, we multiply by g. And the f itself has a different meaning here. So the f here was the one that was in the state transition model. And the state transition model was linear, so I had an f. I had a linear matrix that related the two variables. But here, the f is something different. Is what? How do I calculate here the f? Where do I get the f from? From the Jacobian. Okay? So I compute the Jacobian of this variable with respect to the x. This is the f, capital F. Yes, Muhammad?
What's the difference between lowercase and f small and f capital?
F small and f capital. F small is the nonlinear function itself. Okay? It's the state transition model of the system, and it's a nonlinear function. It has sines and cosines and stuff like that. The capital F is the linearization of it, the Jacobian of it. Okay? So it will be a matrix. It will be an n by n matrix. Okay? Clear? What? That's exactly what I said. It's at home. You already have it at home. It's part of the homework. It's just a lot of time because of the differentiation. That's why I left it for you at home, and there are slides. It's not just, it's a solved problem that you can actually practice and you can take your home to look at, the differentiation, so that we don't waste the time here. That's the only reason, okay? But I agree. It's best with an example. Exactly. So that's why, you can practice and check whether you're understanding. And there's nothing else than partial differentiation in it. Okay? But I just wanted to get the whole picture, you know, just without the details of the math, just to connect the big dots. So here the capital F is the Jacobian of the small f. Make sense? What about the G here? Where do we get this from? How do we get this matrix? G. This is the definition of it. How is it defined? So what is the difference between the G and the capital G and the capital F? Not clear? What? What is the only difference here? If I give you a function of x and y. No, if I give you a function of x and y, go back, you know, to math. I give you a function of x and y. It's a nonlinear function, okay? Can you calculate the differentiation of f with respect to x and differentiation of f with respect to y, right?
Yes.
Yes or no? Yes. So you have two different things, right? If you calculate the Jacobian, which is the partial differentiation of the f, with respect to one variable, so the f itself, let's go back to it. Let me just remind a little bit here. So the f itself is a function of three variables, the xk minus 1, the uk, and the vk. If you take the partial differentiation with respect to xk minus 1, this is what we call the capital F. If you take the partial differentiation, or the Jacobian in general, with respect to the vk, we call it the g. So that's the difference between the capital F and the capital G, okay? Just the partial differentiation of f with respect to different variables, okay? So here, the capital F and the capital G are the partial differentiation of the small f, the nonlinear function, with respect to the x variable and the v variable, okay, which is appear in the nonlinear state transition model, okay? So this is usually we compute on the side, okay, maybe symbolically, and then you can always use it. So that's exactly what you have in the assignment 5, okay, that's already on Blackboard, that you can play around and see actually, this is already implemented for you. If you really, I totally suggest that, you know, you go back and try to actually practice yourself computing the Jacobian, okay, and you'll see, okay, it's actually not that hard. The correction step, okay, is also very similar to, okay, the standard Kalman filter. To remind you of the standard Kalman filter, first, in order to so we computed the new update of the mean and the covariance by these two equations, and they are exactly the same. Okay, so that's one thing. When we computed in this step the innovation, so the beta hat here was called the innovation, which was the difference between the z and our predicted measurement. So when we computed here, we used the H matrix, okay, which is that comes from the measurement model. However, when we computed here, we used the nonlinear equation. So that's the first difference. Sorry. And then afterwards, when we updated the S and the K, we used here the H that comes from the model, okay, and we used the R that is from the noise of the measurement. In this equation, we update the S. In the first term, you see it's exactly the same. And then afterwards, instead of adding the R, we multiply before and after by the L, similar to what we did in the previous slide by using the G. Okay, we use here the L. What is now the H and the L? Now they are just the Jacobian of another function, which is the H function, with respect to X and with respect to W. Okay, so you see the only thing that changed here. Okay, so that's that we introduced two new the H and the L. So the H matrix that came from originally from the state transition model, which was linear. Now I have to compute it every time step. I have to linearize the system every time step, and I have to compute. And there was introduction of this L variable, this L matrix, just to take into account that the noise itself appears nonlinearly in the equation. Okay, so this is in the end, the extended Kalman filter equations. Okay, and they're not really that much different from the Kalman filter, and that's why actually, you know, they are, you know, the favorite of so many people, okay, to deal with nonlinearities. There are more complicated ones, okay. In case you look at, so there are some stuff called particle filters, some stuff called the unscented Kalman filter, UKF, not EKF. Just keep them in mind. If you see them somewhere, they are different from the EKF. Okay? The EKF is usually the easiest version of all of these. And this is the block diagram so that you can take a look at home. The only thing that changed, so this was the standard Kalman filter I showed you earlier. And this was how it changed now is that we have these two blocks, which are the linearization, and I'm using this linearization every time step, okay, to update. A lot of stuff, okay. So now let's get, with the example. So the application, Muhammad, okay. So this is the application now of what we discussed, okay. So we're gonna start with something that we already looked at a lot in the course, which is the IMU. This is a crucial part of any UAV, as you all know, okay. So how can we take the IMU and fuse all of the information into it so that we can get out of it something useful, okay. So now this is the application of the localization, okay. Everything on the slide here should make sense to you, okay, from topic 2 and from topic 3, okay. But of course, it's been a long time, so I just need to remind you of it. So first of all, this is the kinematic model we're going to be using to represent what we want to estimate, okay. So we have an IMU, and the goal in this slide or this part is that we want to estimate the orientation of the IMU. Okay, I want to know how the IMU is posed. Okay, from the measurements that from what I got. So I measure from it 3 accelerations, 3 gyroscopes, and 3 magnetometer values, and I want to use all of these 9 values to convert them to something that tells me how the IMU has an orientation, only orientation, not position. Okay, so we have only the orientation of the IMU. Okay. So if your IMU is part of a phone, then actually what you get from the IMU is same as the orientation of the phone. If your IMU is part of a UAV, then also the orientation that you're getting is for the UAV. Okay, assuming of course the IMU is fixed to the UAV or fixed to the phone, okay, which is usually the case. Make sense? Okay, so this is what we want to do. We want to estimate the R. You all know that. Remember, the R was part of the. We said it's a special orthogonal group. It was a 3x3 matrix. Okay, that was not. You cannot independently choose all of the 9 numbers. They have constraints and so on and so forth. And the equation of motion of how R is related to the omega. You remember what was the omega? What was the omega here? The angular velocity. And what is the square of omega? What was this notation? Square omega. What is it? It was the skew symmetric form of the omega. So it was the 3x3 matrix that was skew symmetric. Okay? And then you multiply by the 3x3 matrix, which is the R, and this is the R dot. Okay? So this is the equation that we have. Okay? So you see, this is the differential equation. It's like x dot is equal to some function of x and u. Okay? So the u here, the u variable is the omega, and the x variable is the R matrix. Okay? Of course, this is very complicated to use the R. Okay, that's why we're going to do something similar in a bit. Okay. How many sensors do we have here? First of all, we have a gyroscope, and to remind you, the gyroscope we modeled it earlier as that I'm measuring the angular velocity of the IMU, but not only that, I also have some bias for the gyroscope, and I have some noise eta. Remember that equation? There was also another one missing here, which is there was an A matrix or an S matrix or an M matrix, something like this. Misalignment and stuff like that, right? Here we're going to assume, okay, that we don't have any misalignment. The IMU has been perfectly calibrated. Okay, so all of this stuff that for the matrices we're going to assume it's gone. Okay, so I'm measuring here the IMU plus some bias and some noise. So I'm measuring the angular velocity with the gyroscope plus some bias and some noise. In the accelerometer, I'm measuring, okay, the acceleration of the device itself. We're going to assume that the device is not accelerating, so you're actually just rotating the drone or something, or the phone like that. So it's not doing any acceleration. And you remember what was the true thing we're measuring? If we don't have any acceleration of the body, we measured gravity, right? If you remember, we were measuring the gravity in the body frame. Okay, so that's why we multiply the gravity here by the RS with respect to B. Okay, so this was the measurement model of the accelerometer, and the magnetometer was also given by this measurement model. Okay, so I'm measuring with the magnetometer the magnetic field of the Earth, okay, or of the surrounding, so this beta, and I'm also measuring it in the body frame, so I have the R here. Okay, so now let me ask you, so these equations 1, 2, and 3. Are they linear or non-linear? Linear or non-linear? Yeah, they are non-linear, okay? You see here, I have a multiplication of the x. So the x here we're talking about, we want to estimate, is the r, is the rotation matrix. So the x and the u are multiplied together, so that's already non-linear. That's one. And you see here, for example, the r, the x, appears also non-linearly in the equation, and here appears non-linearly, okay? Especially because I don't even know the beta and the g. That's another problem, okay? Okay. So you see, the models are usually non-linear like that, okay? What we're going to be, so these are all of the information that we have about the IMU. We know that the eta g, okay, is noisy, and we have, let's say, for example, the covariance of it is, we call it CG. The accelerometer is also noisy. We call it, the covariance of it, CA. And the WM is the noise of the magnetometer, and we say, okay, it has a covariance CM, okay? And all of the three noises, they have zero mean, okay? So usually we call this white Gaussian. It's just a Gaussian, but without any mean. They're just, the value I measure and plus or minus something. Okay? The IMU itself has biases, okay? It's not perfect. Okay, I have a bias here, the BG, the BA, and the BM. These are biases. And the gravity and the magnetic field, the gravity itself, we know, okay, it's 0, 0, and gravity is pointing downward with some constant value. We're going to assume we know that G value exactly. But if you remember from the magnetic field of the surrounding, it's usually very hard to know. Okay, you remember we discussed it a long time ago. So this is what we have. Okay, so there are many choices that you need to take into account to actually solve this problem. Okay. So this is just a general overview of how people actually solve this problem. Okay, and by making these design choices, you can actually get different algorithms and different performances. The first one is that, do I make the orientation? Do I describe the orientation by rotation matrices or Euler angles or something else called quaternions? So quaternions, we never discussed them in the course. I mentioned them sometimes here and there. Okay? But usually in real applications, a lot of people use quaternions. For example, the Ardo Pilot or the PX4, the flight controller, actually implements the algorithm with quaternions. Okay? The rotation matrices, okay, they are, as I showed you, they are very compact. They describe the orientation very nicely. The equations are very easy, to look at, but they are hard to work with. Okay, so they need special mathematics that that needs to be taken into account. Euler angles are very easy to understand, okay, because you have the three angles. They're just three numbers. Okay, however, working with them, you get all of the nonlinearities I'm going to show you today. Actually, today we're going to be doing stuff with Euler angles. So what you have in the assignment, you're going to be solving this problem using Euler angles. Okay. And one very important point is that, do we include the bias or not? So we said here that the bias is part of the problem, right? So do we actually know the bias or not of the sensor? Do we know the bias? We know the bias.
Given.
Sorry? Given, or it's an unknown?
Isn't the bias like threshold where it counts or not?
No, the bias was, for example, you take the gyroscope and you put it on the table, so it's not moving. And you measure the values, and you find that the omega x and the omega y and the omega z have a value of 3 and 4 and 5. You should expect them to be 0, have a 0 mean.
So
but
bias, you said that.
the bias is, you say, okay, maybe I take the mean and I calibrate it, right? So that's correct. That's exactly what we did earlier. If you remember when we had the gyroscope calibration, we were removing the bias by just putting the gyroscope on the table, computing some time, and taking the average of that. That removes only the static bias. If you go back to the slides when we discussed the IMU, we said that the bias itself of the gyroscope depends on more stuff. For example, temperature. It depends on acceleration. It depends on more effects. So in real life, the bias here we don't know. The gyroscope bias is really not that important. Okay? You can actually assume it's 0 by doing proper calibration. The accelerometer, you can also assume it's 0. The magnetometer is the one that's really very important. Why is that? Does anyone remember why?
A lot of things that affected it.
What changes does anyone remember what was the experiment we did in the class here? To actually demonstrate that the bias here gets changed, of the magnetometer especially?
Electronics,
Exactly. What did we call these effects? Does anyone remember? They had a name for the magnetometer. Soft iron and hard iron. Does that ring a bell? Soft iron effects and hard iron effects. What are the soft iron and hard iron? If you take the magnetometer and the magnetometer itself, which is put on the drone or your phone, and you take the IMU and you place it next to something that has metal in it, you get an effect, you get a bias here. So in real life, the magnetometer itself, we cannot just assume the bias is 0. We can do that for the accelerometer and the gyroscope, but the magnetometer is not. Okay? So if we don't know the bias of the magnetometer, a solution of it is to estimate it, okay, with the Kalman filter. Okay? So that is here how we can actually treat with the bias. You can first either exclude the bias or include the bias. Okay? And in that case, it becomes actually a little bit more involved. I'm going to show you here in the slide both actually. Okay? One with the bias and one without the bias. And the last point is that discretization. Okay? Remember that usually you'll find that we started from a differential equation. Okay? X dot is equal to some function of x. And we discretize it so that it becomes something that's xk is equal to some function of xk minus 1. So we have usually, how do we go from the continuous equation, the differential equation, to the difference equations or the discrete models? This is usually a choice that you can make. Okay? And depending on how you choose the discretization, you can get different performance. Okay? So this is in general, so this is just a general discussion. And now what are we going to do here in the remaining time? Okay, I'm going to skip this part now. So let's see, this is the KF version 1. Okay, no, actually, let's do this. Okay. So this is what we're going to be doing here in the first step. Okay, so I'm going to show you two different EKFs today. The first one, we're going to be estimating the roll, the pitch, and the yaw angles of the IMU, along with Bx, By, and Bz, which are the three biases of the magnetometer. Okay? So the x vector that we want to estimate, how big is it? What's the dimension of it? What's the dimension of x? The state is 6, exactly. Okay? So now we need an equation that has x dot, okay, that relates the rate of change of the state, so that we can use it and discretize it and do with it the Kalman filter. The equation is given by, so alpha here, we're going to be calling alpha, okay, the roll and pitch and yaw angles together. Okay, so these are 3 angles. So alpha here is 3 angles together, and the Bx, By, and Bz are simply the beta together. Okay, so we have these 3 vectors. Alpha dot, which is the rate of change of the roll, rate of change of the pitch, and the rate of change of the yaw, are related to the angular velocity by this matrix T, given by this equation. And this is not the first time you see this. Actually, we did it before. There was, in topic number 2, you need to go back to that slide. And you're going to find that when we introduced the roll and pitch and yaw angles, we said that the rate of change of these angles are related to the angular velocity by this matrix. Go back to that discussion, okay? And just to remind you a little bit of what we discussed there, you remember here when we have a division here by cosine theta, right? Yes. And the division of cosine theta, cosine theta can be 0 at what angle of theta? Cosine theta 90. Is 0 at 90 degrees or negative 90, which means that you're pointing up or pointing down. Yes. What happens here when you have theta equal to 90? You have the gimbal lock, exactly, what we discussed earlier. Okay, so go back to the slides and remind yourself. The R itself, the rotation matrix, now becomes actually a function of the alpha, of the roll and pitch and yaw angles, and it's given by this expression, which we also discussed earlier. Does anyone remember how we got this rotation matrix? How we derived it? In topic number 2.
You multiply rotation.
Rotation of the matrices for each rotation.
Exactly. We had the rotation around Z for the yaw, multiplied by rotation around the Y for the theta, for the pitch, and then rotation around the X for the roll. And then we get this matrix. Okay. So now do you see R is a nonlinear. Is this linear or nonlinear? Definitely nonlinear, okay? For 2 reasons. First of all, you have sines and cosines. The sines and cosines and all the trigonometry functions are already nonlinear by themselves. But worse than that, you even have sines of theta multiplied by sines of phi and sines of psi and so on. So you have even a combination, multiplication of trigonometric functions, which means that's even more nonlinear. Okay, so being nonlinear is already enough, but you can have easy nonlinearities and hard nonlinearities. This is complicated stuff because you have multiplication of trigonometric functions. So this kinematic model, is it a linear equation or a nonlinear equation? Nonlinear. So you see here, this equation is simply x dot is equal to a function, nonlinear function, of x and u. Is that clear? Make sense for everyone? The gyroscope and the accelerometer, we're going to be assuming it's not biased. Okay? There is no bias in it for simplicity. In the first EKF, now we're going to be showing. And for the magnetometer, it has a bias. Okay? And the bias itself of the magnetometer is actually one of the states that we're talking about. So you see here, this is actually a measurement model that's nonlinear, and this is a measurement model that's nonlinear. Okay? So I have here two measurement models that are nonlinear, and here I have a state transition model that's nonlinear. Okay? So this is the relation between the real application and the theory that we were talking about. Now the question is, how do we actually implement this? Okay? What we need to do, so now if you take all of the equations now, you actually can put them something like this. There is something that we haven't discussed here, which is we know that alpha dot is related to the previous state and the omega by this equation. A question is, what is beta dot? What is the beta itself? What was beta here in this slide? What is beta here that we want to estimate? What magnetic field? Of the Earth, exactly, or the surrounding, exactly. We want to estimate this parameter, okay, without the bias even. So here we just something I saw. I made a mistake here. So in this case, we're not taking the bias of all of the sensors, okay, and the magnetic field itself of the surrounding is the one that we include in the state here. So what is this magnetic field? Is it a constant or is it something that's varying? This magnetic field of the surrounding, including Earth. It varies, right? With time?
I think with position.
As you move along Earth, right? Yeah. As I move from from here to London or something, go back and forth. If you do something that's if you have your UAV and you're covering a lot of distances, then the magnetic field changes with time. But if you have your IMU or your robot inside of a room, does the magnetic field change with time?
Yeah, if it's insulated, no.
If you get near stuff, okay, then also it changes in that sense. But when it changes, does it change very rapidly or very slowly? What we're going to be doing here is that we're going to be assuming that beta is a constant that's changing very slowly. Okay? And thus the model for the beta dot equation, will be given by something called a random walk. Okay? So the random walk is usually something that you do in state estimation, that you can assume if you have a variable that changes over time very slowly, okay, but randomly, and something you don't know how it's going to change, so it's completely random, you can simply express the differential equation by that. You say that b dot is equal to 0 plus some white Gaussian noise. Okay, so it's changing, okay, but very slowly in a random way, and how fast and how slow it's changing, I can control it by this Q, okay, covariance. And if you discretize this equation in time, it's very easy. You just get that the bk is the last value plus or minus some noise variable. Okay. So it's not you're saying that it's not always constant, but it's allowed to change, okay, very slowly. And that's exactly what we're going to be doing here for the B. We're going to be assuming that the beta dot is given by some noise. Now take all of these pieces together. Now you have an equation of this format. Okay? So Muhammad, this is the example you were asking for. So this is x dot is equal to f of x and u and eta. Okay? So this is the two x's. So this is the x vector that we want to estimate. We want to estimate the alpha and the beta. What is the alpha? What is it physically? What does it represent?
It's motion. No, it's
The Euler angles of the IMU. And what is the beta? The magnetic field of the surrounding. That's what I want to estimate. And how are they related to each other? How are these variables related to each other? Related by these two equations. So I see here I have the T of alpha. The T is the matrix that we discussed earlier, the one that has sines and cosines. And it's multiplied by the omega m. So omega m here is the measured input from the gyroscope. And I have here some noise and some noise here. This is the noise of the gyroscope. This is the noise of the magnetometer. This is the state transition model in the continuous time format. And this is how we put it into the discretized format. Going from here to here is left as a homework for you. Okay? We did it twice in the class when we used this expression. We don't have it here. We remember when we had x dot is equal to xk minus xk minus 1 divided by delta t. And we just played around with the equation. This is how you can get this equation. Okay? So now you see the discretized model written in that format is xk is equal to f of xk minus 1. So f here, I have a function of xk minus 1. You see here I have alpha k minus 1, beta k minus 1, alpha k minus 1. These are all of the previous time step states. I have the u. The u here is the measured gyroscope. And the eta here are the two noises that you see here. The measurement model itself is also a nonlinear function. Okay, it's given by I used for the z. Okay, I use the accelerometer and the magnetometer. So the way this Kalman filter is set up is such that the control input that we use here in this step is the gyroscope, and what we use in the prediction step is the accelerometer and the magnetometer. So is that clear? So we use the gyroscope at one stage in the prediction, and we use the magnetometer and the accelerometer in the correction. Okay. So this is the Kalman filter. Yes, Mahsen.
اقدر اطلع عرض مشروع التخرج
Sorry?
للفخ المشروع
Could you?
زملائي يبون اساعدهم مشروع الفخ
I cannot hear you.
عندنا عرض مشروع التخرج اليوم
Okay.
وزملائي يبوني اساعدهم الفخ
Go. You can go. Okay. Is that clear for everyone? So this is the equations. Now, what is the Kalman filter equations itself? We don't need to discuss them, right? Because we already identified the f. So this is the small f for this problem. This is the small h for that problem. Now what we need to do to implement the Kalman filter, we need to just to compute the Jacobians. Capital F, capital G, capital H, and capital L. Okay? This you can do very easily in MATLAB. You know, if these are very nonlinear functions. You remember I told you earlier, right? You can, in practice, you never use pen and paper. You can just use computer to actually do the differentiations. Okay? Numerically or analytically, both are okay. And you actually have this implemented in the assignment. Okay? So I urge you all not just to use the assignment as a black box. Go into it and take a look at it so that you can really understand what we're talking about here. Okay? It doesn't require you to solve the assignment. You don't need to do that. Okay? But you're not going to understand any of that stuff. Okay? If you just skip this, the MATLAB file that you have. So inside of the MATLAB files, these nonlinear functions are implemented. Okay? And the Jacobians are calculated there. Take a look there how you compute them. Okay? And afterwards, you can use the Kalman filter. Done. Okay? So we don't need to tell me, how to use the Kalman filter. They're just the equations that we had. You just implement them in the Kalman step, the Kalman update. So sorry, the Kalman predict and the Kalman correct, similar to what you did in the last assignment, and the algorithm just runs again and again. Okay? So another formulation so this is a more extended version of it. So this is another EKF. So you see here, this is the EKF formulation 2, where in this case, the biases of the gyroscope, the accelerometer, and the magnetometer, we can take it into account. You see how much the state vector becomes now? It will explode now. Okay? Because originally I had the alpha, the Euler angles were 3 variables. So roll, pitch, and yaw. The beta were 3 variables, b and x and b and y and b and z. And the biases now, each one is 3. So I have 1, 2, 3, and 4, and 5. Each one of them is actually 3 variables. So in total, I have 15 states. Okay? And now in order to model it, I need to have a model for the 3 biases. And that's also very easy, because I can assume that these biases, they just have some random walk, similar to what we did earlier for the magnetic field, and the measurement model only gets a little bit, bigger. Okay, and still you can implement this very easily. Okay, you just update the functions, and the Jacobians will be bigger. Everything will now be 15 by 15. Okay, so they're just big matrices, and that's it. Okay, so everything we discussed today was all the extended Kalman filter. You have an application of it, okay, which is in this slide. You have two applications, two different ways of how we can formulate a nonlinear function, nonlinear state transition model, and a nonlinear measurement model, okay, for the same problem, which was for the IMU estimation. Now this is implemented. You'll practice with this at home, okay, with assignment number 5. So don't start with the assignment immediately. Start with the assignment, but keep these slides next to you so that you can compare what's going on in the code, okay? So that you can really understand the application of that stuff. Yes, Mohammed.
So we took two methods to apply the AKF, right?
Yeah.
Formula 1, Formula 2. Is there any? It's an old. I think it's not an old, but like it's already been here. The Kalman filter. So is there any library that's famous to?
So many libraries. Yeah. So many libraries. Yeah. Kalman filter is very fundamental. That in MATLAB it's just one line. In MATLAB libraries it's just one line. In so many libraries it's one line. And now with ChatGPT it's even easier, because you can translate it into any language. You're not bound actually by the libraries themselves. So let's say you have your code. For example, you're working on a microcontroller, in your project, and you want, just a small Kalman filter that you implement there. Okay. So the equations of the Kalman filter themselves. That's actually a very good question, because the equation of the Kalman filter itself, whether they are the standard version or the EKF version. I'll show you now the EKF version. So these are the equations of the extended Kalman filter, which is more general. Sorry, this is the extended Kalman filter. The standard one, the linear version, is even smaller than that. In the last assignment, you all implemented the equations of this one. And I'm pretty sure the first impression when you implemented them or used ChatGPT to implement them is that you're actually surprised. There are just 2 lines of code and three lines here, or 5 lines here. So that's it. That's the Kalman filter itself. So it's implementation-wise, it's very easy. The extended Kalman filter, you just have 2 extra stages, 2 extra equations in each step, where I compute the Jacobian. And even the Jacobian itself, computing it by the computer is no big deal. You just need a library that allows you to do actually this stuff. There are some libraries for automatic differentiation. MATLAB already has that. You can actually have a differentiation function. You give it a nonlinear function, and you differentiate, and it will give you the Jacobians all symbolically even. And numerically, it will even be faster. So differentiating a function on a computer is not a big deal. So what is the biggest problem in implementing the Kalman filter? Can anyone say that? So that's from an engineering perspective now. Forget about all of the math and from an engineering perspective. What can you take out of this whole class? This whole topic actually. We're done actually by topic 4. Okay? That's it for the localization. What do you get out of it?
How to know the output accurate?
What?
How to know the output is accurate enough?
Okay, that's one. The estimation itself, okay, it's crucial. There is no robot without the localization, right? You cannot do anything with a robot. And I'm pretty sure you all faced some of your problems in some of your projects this semester, right? If you have a robot or something that, you have the sensors on it, and usually what the sensors measures is not exactly what you need from the robot, okay? For example, the easiest problem, is the IMU. That's why we took the IMU now. The IMU is measuring for me accelerations, gyroscope, okay? So accelerations, angular velocities, and magnetic fields. How is that related to how the IMU is oriented? This is the whole math that you need in that to actually do this. Okay. So the modeling part of that you relate the sensors to the state that you want to estimate. This is usually the biggest problem. Okay. So libraries are already available, yes. What is the state transition model of your problem, and what is the measurement model of your problem? This is usually the open problem. It depends, and it requires a lot of requires the engineering efforts. Okay.
Is it like optimization issue or?
No, it's not optimization.
No, I mean in the model, like how to simplify it so it can be faster.
That's exactly the thing. Yeah. so there are two things now. There are three things on the table now. First one is that if I am given a problem, and this is exactly what we've been doing today. This is the problem. I want you to estimate the orientation of the IMU. What is the state transition model and the measurement model that I can give to the Kalman filter? And I give you two ways depending on some assumptions. So in the first formulation we did today, I assumed that these are my states. And in the second formulation, I assumed this is my model, depending on, because I have more states. So in the second model, I had 15 states. In the first model, I had only 6 states. That's a choice. It's the same problem, and I have two different formulations. Okay? Of course, this one will be better, and I think in the assignment you're implementing actually both, and you're going to be comparing. I think so, if I'm not mistaken. Okay? If not, I think you're going to be implementing the second one alone. Okay? But you can actually play around with it and see. You can compare the two formulations. So the same problem, same sensor. You have a company, you implemented the first Kalman filter. You have another company who implemented the other Kalman filter. Performance is different. Now there is something here related to accuracy and speed. Which one do you think is faster than the other as an algorithm? Who says the first formulation? So the EKF, we have EKF formulation 2, and we have EKF formulation. What happened? And we have EKF formulation 1. In the first one, we had the Euler angles and the magnetic field. And in the second one, we had Euler angles, magnetic field, but also the 3 biases. Who says that the first one is faster? Who says the second one is faster? Why? Less dimensions, less states. So we had 6 states versus 15. Less states means what? Why? Memory-wise, yes, you require less stuff, less information to store. What about speed? Why? If you go to the equations of the Kalman filter, which are this one. Let's take the standard one for simplicity. What are all of these boxes doing? They're doing matrix multiplication, right? And you also have here something like matrix multiplication and also matrix inversion. If you're inverting, in the first problem, some of the stuff here we have 6 by 6 matrices. And in the second version, we have 15 by 15 matrices. Which one is faster to use? Of course, the 6 by 6. Okay? So it definitely is faster. Which one is more accurate?
The second one.
Why?
It includes the bias.
It includes the bias, exactly. The first one, okay, in the first formulation, which is what we did here, in this expression, we assume the bias is just 0. What if the true IMU does not have a bias of 0? Then it's a problem. It's just an approximation. Now the real problem in real life, is the bias 0? No. The bias changes with out of factors. We go back to topic number 3, we discussed these factors, So in real life, when you implement the second algorithm, you'll find that actually the second algorithm is more accurate. Okay? Now there is a third problem, okay, which is more even crucial. If I tell you, okay, you have 2 algorithms, one for Muhammad and one for Jess. Okay? I'm testing both. Okay, so I use the first algorithm and I do I put the robot like that, and I do different orientations and I get different values. You should be giving me different, curve than you, right? Which one is the correct one? You're saying yours is better, right? So let's say I assume Jassim has the second one and Muhammad has the first one. Muhammad is faster, which means for example, I can run it at 1000 hertz, but you're slower, so I need to run it at 100 hertz maybe, just approximately. But you're more accurate. How can I know actually that you are accurate? Where is the ground truth here?
I think it depends on the application. So for example, in the aircraft, we have 2 types of slow, one that requires slow response but accurate.
Okay.
Like the altitude, the heading. It's okay to be slow, but it has to be accurate.
Okay.
So we take the second formulation.
Okay.
But like roll bridge, I think the first is going to be, for stability, is better.
That's a good point. Depending on the application. Which one? But that's related to the speed. The accuracy is another problem. In all of what we've been doing in topic number 4, we have no idea what the true values are. Okay? Don't get confused about what we've been doing in the simulation. The simulation is just, it's all made up, right? I was actually giving you the true value. For example, what you had in assignment 1, you knew where the true robot is, but that's because you were actually simulating it in the computer. In real life, we don't know where the robot is. And that's actually another problem now. Okay? So if there is an error, we would never know. There are some ways how you can actually check whether the Kalman filter is correct or not, or it's consistent or not. We haven't discussed that. But in real life, we have no idea about where the true robot is, unless you do some experiment. For example, let's say that you have a room with cameras, and you put on, for example, on your robot some markers, and you use this as the ground truth. Down in the lab, I'll show you inshallah next week when we go to the lab. We actually have a room like that. It's called a motion capture system, and you can actually put on your robot some markers to actually get exactly what the ground truth is. Instead of using this for control, you can actually use it to tune the Kalman filter, and then you can take the Kalman filter and go outside in the real world. Okay? Is that clear? So that's it. Any questions? Okay.